When we walk through a modern city, we react to the surface. We see the aesthetics of a glass facade, the arrangement of a high-ceiling lobby, and the comfortable, climate-controlled spaces we live and work in. We experience the architecture. But this diagram maps the actual engineering workflow, showing that an architect's plan is merely the initial input. Moving from a vision to a physical reality requires passing the design to structural engineers, who must calculate for safety, standard of practice, and optimum economy. A completed building is an assemblage of overlapping systems. Above the spatial system, the M&E system manages air, water, and power. To keep these suspended, the bottom anchor layer, the structural system, collects all accumulated loads and safely transmits those forces straight down into the earth. Achieving this downward transfer requires constant negotiation. Engineers balance four competing pillars: the function of the space, the safety of the load transfer, strict economy, and long-term maintainability. Over-index on one, and the building becomes too expensive to construct or entirely unsafe to occupy. This graphic classifies the four overarching families of structural systems available to solve that problem. Depending on the spans required, engineers choose between solid wall bearing systems, tension-reliant tent and cable systems, curved shell systems, or the highly modular skeleton structure. In modern commercial construction, the skeleton structure is the dominant choice. It relies on a distinct, interconnected grid of rigid members to manage the invisible, constant pull of gravity. This diagram isolates how a skeleton routes gravity. Step 1. Slabs collect permanent dead loads and temporary live loads. Slabs push this weight horizontally into beams. Beams funnel forces down vertical columns. Finally, the foundation spreads this massive, concentrated load evenly into the supporting soil. Inside those beams and columns, materials fight two types of physical stress. This diagram compares them. On the left, a tensile load actively stretches a member outward. On the right, a compressive load pushes inward, threatening to buckle the material out of alignment. If a beam stretches past its limit, or a column buckles under the crushing weight, the continuous pathway to the earth breaks. The building fails. To prevent snapping and buckling, engineers select materials with highly specific properties. This diagnostic table highlights the contrast. Timber is lightweight and easy to construct for residential use. Steel offers an extreme strength-to-weight ratio needed for high-rise commercial structures, despite being far more expensive. But the most heavily utilized material in modern engineering doesn't rely on a single physical property. It uses composite action, intentionally combining two flawed materials to cancel out their individual weaknesses. This visual breaks down the equation. Normal concrete has massive compressive strength but weak tensile strength. If pulled, it snaps. By embedding a steel grid into stretching zones, engineers create a unified block. Concrete absorbs crushing forces downward, while steel resists tearing forces pulling apart. When this composite ratio is off, the material provides warning signs. This graphic maps 7 specific fracture patterns, read like a diagnostic chart. Vertical flexure cracks show where the member bends too far. Diagonal shear cracks reveal where opposing internal forces slide against each other. To eliminate cracks, the industry developed pre-stressed concrete. As shown here, engineers used tightened steel cables to intentionally squeeze the concrete from both ends. Placing the beam under extreme active compression in the factory neutralizes the stretching forces of the building's weight later on. We tend to think of steel and stone as static objects. In reality, they are meticulously engineered technologies, calibrated to manipulate physical forces right down to their internal geometry. Before a single piece of steel is ordered or a yard of concrete is poured, these material tolerances have to be proven on paper. This document defines the codes of practice, the strict legal and mathematical rules dictating how much stress a structure can take. In 2010, the industry shifted from legacy British standards to the Eurocode, recognized as the world's most technically advanced structural code. This flowchart illustrates the Eurocode's modular architecture. Engineers start at the top with EN 1990 for baseline safety and durability rules. They calculate environmental loads using EN 1991, then drop down to specific material design codes like EN 1992 for concrete. Reality translates into variable notations.
G quantifies unmoving dead loads. Q handles variable loads like wind. Importantly, engineers never build to baseline theoretical limits, K. They apply safety factors to arrive at D, the design value, guaranteeing a built-in buffer against the unpredictable real world. A completed building is the direct physical manifestation of these equations. The structural engineer stands exactly at the intersection of abstract mathematics and raw gravity, ensuring the spaces we live in remain safely, quietly anchored to the earth.